Hi, in this video we will be doing problems related to dynamics from this book. It's called Engineering Mechanics Dynamics 14th edition by Hibbeler. The problems that we will do is from chapter 22.1. It's related to undamped free vibration. So in this chapter, we will be discussing and solving problems related to free vibration. Free vibration occurs when the motion is maintained by gravitational or elastic restoring forces, such as the swinging motion of a pendulum or the vibration of an elastic rod. Undamped vibration exclude frictional effects in the analysis. But in reality, both internal and external frictional forces are present in the motion of all vibrating bodies is actually damped. The simplest type of vibrating motion is undamped free vibration. So it's important to know that undamped free vibration, undamped mean that we are not considering the frictional, internal and external frictional effects on a system. Free vibration, this vibration happened due to gravity and or the elastic force, in this case the spring. So the first problem that we will discuss is 22-1. So here we are told a spring is stretched 175 millimeter by an 8 kilogram block. If the block is displaced 100 millimeter downward from its equilibrium position, and pay attention to the word phrase equilibrium position, and given a downward velocity of 1.5 meter per second, determine the differential equation which describes the motion. Assume that positive displacement is downward, so that forms your reference. The downward is positive. Also determine the position of the block when time equal 0.22 seconds. So first thing, let's write down what is given. So it's important to write down what is given, then we're going to sketch what is given to us. So here we are given a spring. A spring is a device that stores energy. And here we're talking about elastic energy. We are told that this spring is being stretched. So the spring had an original length, and due to the 8 kilogram block, that spring got stretched a distance of 0.175 meter. So that is the change or the deformation of the spring. So as we said, the spring got stretched due to the mass 8 kilogram. The 8 kilogram block displaced an amount of 0.1 meter from the equilibrium downward in the positive direction. And here we said that while we are displacing the block 0.1 meter, the block attained or reached a velocity of 1.5 meter per second. Here in these two situations where 0.1 meter below the equilibrium and it reached 1.5 meter per second, these are called your initial conditions. And what happened in here is your spring got stretched, and then due to the block, then the block got displaced. While we are displacing the block 0.1 meter, it reached this velocity. And once these two conditions met, we start at time 0, the block will be released and the block will start to vibrate. Here we assume that the positive displacement is downward. So here we're asked to determine the differential equation that represent this motion with these given information, And we want to determine, when we found the differential equation, we want to determine the position of the block at time equals 0.22 second. So this is our spring that we're talking about. This is the normal, unchanged spring length from here to here. Now, in here, as you can see, we have the same spring, but the spring got stretched, and it is stretched due to the 8 kilogram block. Okay. Now, this was the original length. And due to the block, it got stretched an amount of 0.175 meter. So now the spring and the mass right here, this become our equilibrium position. And here we can zero our location. And we said that downward is positive y direction. In here, in this third one, we displaced the block of mass with it, the spring, an amount of 0.1 meter at 0 second. And as we are displacing the block attained or reached a velocity of 1.5 meter per second at 0 seconds. Once we reach these two conditions, we release the block. Now, the spring will start to do its job. The spring will use its elastic energy to bring back the spring to its original position in here, back to the equilibrium position. So the block will exert a force opposite to the direction of the displacement. And that's what we're going to have in here. And then the block will move upward to the equilibrium position. But what will happen, it will continue further above the equilibrium position, and it will continue vibrating back and forth, back and forth. Now in this, we are not analyzing the damping or the friction. Here we call it undamped. So in reality, this thing will vibrate, and it will and the spring and the mass will come back to their original situation at the equilibrium position. All right. So first thing, let us draw the free body diagram of the spring and mass at their equilibrium position at 0 meter. So at this position, we are not moving. So here we will have our 8 kilogram. So, and we said that downward is positive y direction. Now the 8 kilogram, we have a force due to gravity, which is mass times gravity. So this is the weight of the block. The spring is obviously pulling up, and that we call it the force of the spring. All right. So now we say that the sum of the forces in the y direction equal to 0. And remember, downward is positive. So m times gravity, which is downward, positive, and force of the spring is upward, because force of the spring is always in the opposite direction of the displaced or stretched spring. So what is the force of the spring? The force of the spring is the spring constant, or the spring stiffness, times how much the spring got stretched. So we have mass times gravity minus the spring constant, or spring stiffness, times y stretch. That is how much the spring got stretched due to the attached block of 8 kilogram, equal to 0. So next, the mass times gravity, we will move this to the other side of the equation, become k times y stretch. So now we are given the mass of 8 kilogram. The gravitational constant, we know it, it's 9.81 meter per second squared. And we are told that the stretch amount is 0.175 meter. So from here, we can find the spring stiffness. All right. So here, when we solve for k and move the y stretch to the other side of the equation from multiplication to division, as we can see in here. So what does this equation tells us? It tells us that the less the spring gets stretched, the more stiff the spring will be, and vice versa. So here we will solve for the spring constant, and we will plug in the given values, which of 8 kilogram, 9.81 meter per second squared, divided by the amount that the spring being stretched due to the 8 kilogram block attached to the spring. So this will give us that the spring constant is 448.46 Newton per meter. So that's how much force needed to stretch a spring an amount of 1 meter. So obviously, if this value is higher, so let's say this one, instead of 448, it's 580, for example. So that means this value stretch will be less because the spring is stiffer. But I want you to pay attention to the y stretch in here. So now we can, instead of solving for k, we can also solve for y stretch. So we can move k to the other side of the equation from multiplication to division, and we will get this equation. So y stretch, this is the relationship that relate how much a spring is being stretched for a given mass and a given spring stiffness. Now we will deal with the spring and mass in motion. So as we are displacing the block below the equilibrium position in the positive y direction. So here let's draw the 8 kilogram, and here we have a positive y direction going downward, and it's moving downward, so it have a positive acceleration. All right, so the 8 kilogram block, it have a weight due to gravity, or force due to gravity, of mg. And as we are displacing the block, obviously the spring will exert a force opposite to the direction of displacement, which we will call it the force of the spring. So here we will say that the sum of the forces in the y direction, and remember downward is positive, is equal to mass times acceleration. All right. So here, mass times gravity, positive, force of the spring, upward, negative, equal mass times acceleration. Remember, the force of the spring is the spring stiffness, which is the type of the spring, times how much the spring deformed in total. So here we will say mass times gravity minus the force of the spring, K, and the first change happened due to the stretch, due to the hanged mass, plus here the y is the amount the spring got stretched due to the displaced block, that equal to mass times acceleration. So here what we can do is we can replace y stretch that we have by the relationship that we discussed in the previous slide. So now we can delete this k with this k, and we will be left with mass times gravity minus mg times the spring stiffness times the amount it was displaced, equal to mass times acceleration. So here we will distribute the negative into the parentheses, so it will give us m minus m times g minus k times y equal m times y. So now positive 1 minus 1 will give you 0, so this will cancel. So here we will left with minus k times y equal to m times y squared. So acceleration, sorry. So here we can rewrite this and take this to the other side of the equation. So mass times acceleration plus k times y equal to 0. So now we can divide mass by in both sides of the equation, and 0 times mass will give you 0, so that's why we have 0 in here. So here we can cancel the mass, and then we can rewrite this equation: acceleration plus k over m times y equal to 0. So the question is, what is k over m? Well, there's something called the natural frequency. And in general, natural frequency tells you how every system, every mechanical system, it have its elasticity. It have its and that elasticity can be represented as a spring, and that mechanical system, or that is made of a certain material, it have a certain mass. So due to this object that have certain elasticity and a certain mass, it have a natural frequency. So for example, like a fork. So when you hit a fork, that fork will, due to its elasticity and due to its mass, it will have a certain frequency to it. Frequency means how many cycles this object can vibrate in 1 second. So every object have its natural frequency. So every spring and mass, depending on the spring stiffness and depending on the mass that we have, they have their natural frequency. So here we related natural frequency to two things: the type of the spring, which is the spring stiffness, or the elasticity of an object that is vibrating, and the mass, or in other words, the mass of the object that is vibrating. So that's why we can relate some mechanical system, and we can model some mechanical systems as a spring and mass model. So the natural frequency is the square root of the spring stiffness divided by mass. So if we took the square of both sides, we can get rid of the square root. So that's what we did in here. So the natural frequency squared is equal to k over m. And this is the k over m that we have in here. So we can replace k over m by the natural frequency squared. So it will be acceleration times the natural frequency of the system that we're dealing with, times the amount this system got stretched, or initial stretched, equal to 0. All right, so right here, what are we dealing with? So this is a differential equation. So what type of differential equation is this? This is a homogeneous second order linear differential equation with constant coefficients. So this right here, that where is the general solution for this differential equation. Now in this video, I'm not gonna go over how we solved this differential equation and we got this answer. And obviously to get, so this general solution is y as a function of time. And this represents the position of the block as it is vibrating. And to find an equation that represents the velocity of the block as it vibrating with respect to time, all what we can do is to differentiate this equation and to give us this. Now remember that sine, the derivative of sine is cosine, and the derivative of cosine is negative sine, and here we use the chain rule. Same thing if we want to know the acceleration of the block with respect to time, we can take the derivative of the velocity function, and that's what we will get right here. And as a side practice, what you can do is you can take the acceleration y double prime and plug it into your original differential equation, and here your position function y, and plug it in here. And when you solve for this equation, you will get the answer 0. So that is a proof that these three equations are general solution for this differential equation. Now these two, a and b, we call these the integration constant. We can solve or find out these a and b values from the initial conditions. So what we will do is we will use the initial conditions at time equals 0 second. So here, the position at 0 second is 0.1 meter, and the velocity at 0 second is 1.5 meter per second. So now what we will do is we will plug in these given values into these general solution to find the equation that represent the differential equation that represent this problem. So we will plug this into our position equation. So initially 0.1, and remember 0 times anything is 0, so that's why I didn't write the natural frequency value. Now here, as sine of 0 is 0, cosine of 0 is 1, so a will cancel, and we can solve for b, so b value is 0.1. And to find the velocity, or to find the a value, let's here find the natural frequency of this system that we're dealing with. So we are given the spring we found the spring constant 448.46 Newton over meter times the mass that is being attached to the spring. It will give us this natural frequency, 7.487 radian per second. So that's how much angle this thing can rotate in 1 second. So we can plug in the natural frequency and the velocity at time 0, 1.5 meter per second, into the velocity equation like we have in here. And as we said, that the sine of 0 is 0, so the b term will cancel, and here we can solve for a. So 1.5 times a, and cosine of 0 is 1, so now we can solve for a. So we'll move the natural frequency to the other side of the equation, from multiplication to division. Plug this into your calculator, and you'll get that a is equal 0.2. All right, so here the a value is 0.2, the b value is 0.1, and the natural frequency, we got it to be 7.487 radian per second. All right, so now for the position function, we can plug in these values into the position function, and that's what we will get in here. Now in the problem, they told us, hey, we want to know the position of the block at time 0.22. Simple. So now let's plug 0.22 into this equation and use our calculator to find the value. So the value will be 0.192 meter right here. Okay. So if you took this function right here and you graph it, so that's what you will get in here. So now let's try to take a look at this function, or this graph that represent the movement of the block. Now here at 0, this 0 represents your equilibrium position. So first thing, let's take a look at this. So from 0 all the way to the maximum point, we call it C. C is the amplitude. That is the highest point. So when we stretched the block, the spring applies a force opposite to that direction, and it compresses the spring to a maximum position, and then it goes down below the equilibrium position to a maximum position. So we want to know what is the amplitude of that. So to find the amplitude, we simply take a squared plus b squared, and a is 0.2 and b is 0.1, and we square them and plug this into our calculator, and then we can get the C value. So here the C value is 0.2236 meter. So that is the maximum displacement from the equilibrium position if the spring got stretched or it got compressed. So remember, we said that positive y direction is downward. So in this direction, point, in the positive direction, it's being pulled. In the negative direction, it's being compressed. All right. So now the distance from the equilibrium to this point right here, this is your B. That's how much it's being displaced from the equilibrium position, 0.1 meter. So from here where you start vibrating the block and the spring mass. Now we start from a point, then we return back to the other point. That's what we call it vibration. You start from a point, it vibrates, and it comes back to where you stretch. So that's the maximum stretch it reach. Then it will be compressed above the equilibrium right here. And then the elasticity will do its job for the spring, and it will bring it back downward to where it was in here. So this is going back and forth. So we want to know how much time it took the mass to start from this position and come back to this position again. So this is what we call it the period. Period is 2 pi because it completes a circle divided by the natural frequency of the system that we're dealing with. So if we plug in the values of 2 pi and the natural frequency that we found, we will get that it takes 0.8392 seconds. That is the time required for the block of mass to complete one cycle. So the frequency is what? Is the reciprocal of period, or the reciprocal of time, which is 1 divided by 0.839 equal to 1.19 hertz. So what does 1.19 hertz means? It means that this is how many cycles this system can do in 1 second. Can you imagine this system do 60 hertz? 60 complete cycles. So this from here, let me try to use another blue. So right here, this one right here, if you can think of, if you took this stretch, you can do it as a circle. So imagine, so this one complete one cycle, right? It starts from a point, which is this one, and it ends at the same point, which is this one, okay? So this one tells us that it need to complete 1.19 cycle in 1 second. What would you say if this system vibrate at a rate of 60 or 50, completing this cycle 50 times in 1 second, or 60 times in 1 second? What would that tell you about the system that we're dealing with? All right, the second problem here, we have a spring has a stiffness of 800 Newton per meter. All right. If a 2 kilogram block is attached to the spring, pushed 50 millimeter above its equilibrium position, and released from rest. Released from rest. Now the previous problem, the block of mass was released when it reached a velocity of 1.5 meter per second. But here you displace the block and then you stop, then you release it from rest. Determine the equation that describes the block's motion. Assume that positive displacement is downward. So first thing, let's write what is given. So here we're dealing with, we are given a spring stiffness, or a spring constant, which is K, which is 800 Newton over meter. Now, we are given a block of mass equal to 2 kilogram. Now, this block of mass got displaced from equilibrium position a distance of minus 0.05 meter. Why is it minus? Why did we write minus? Because we are told that assume positive displacement downward. But here we are told that we pushed the block and mass, fifth block mass system 50 millimeter above its equilibrium, so in the opposite direction, so that's why it's negative. So now let's draw, or let's sketch our problem. So this is our spring. This is the natural length of the spring right here. And this spring, we are told that we identified the type of the spring by its stiffness, which is 800 Newton over meter. This spring got stretched due to a 2 kilogram mass. And obviously, when this mass is being attached to this spring of 800 Newton per meter, it will cause the spring to stretch a certain amount. So why stretch? So now this will become your equilibrium position. And here we can zero our location, and downward is positive y direction. Here the spring got pushed, or in other words, compressed, a distance of minus 0.05 meter at 0 second, and then stops at 0 seconds, 0 velocity at 0 second. So these are called your initial conditions. And as we said, that the spring will exert a force opposite to the displacement direction. So the displacement was upward, the spring will exert a force opposite to that direction to return back the spring and mass back to the equilibrium position. All right, so first thing what we want to do is we want to analyze the spring and mass at equilibrium position at 0. So spring and mass is not moving. So you have your 2 kilogram. This thing is downward is positive. The first thing is mass times gravity, the weight of the block, and the spring will exert a force opposite to that opposite to the displacement direction of y stretch upward. So that will be your force of the spring. So here we can say that the sum of the forces in the y direction equal to 0. So downward is positive, mass times gravity. Upward is negative, so that's the minus force spring equal to 0. And again, the force of the spring is the spring stiffness times how much a spring got stretched due to the spring stiffness and the hanged mass equal to 0. So here we have the mass, the gravity we know, which is 9.81. We are given the spring stiffness. We can find how much this spring got stretched due to the hanged mass. So we can move this to the other side of the equation, and now we can solve for y stretch. So y stretch is mass times gravity divided by k equal to y stretch. So here y stretch is equal to what? 2 kilogram times 9.81 meter per second squared divided by the spring constant of 800 Newton over meter. So now when we plug this into our calculator, it will give us that the y stretched is 0.0245 meter. All right, so now let's take a look at the spring mass as it's being displaced above the equilibrium position at this two initial conditions. So here we have our 2 kilogram mass. Downward is positive, and before I forget, this thing is moving up, so it have a negative acceleration, not a positive acceleration. It's going above the equilibrium, and we assume that downward is positive. So here we have our mass times gravity, and the force of the spring will exert, since this is moving up, the force will or being displaced upward, the force of the spring will exert an opposite direction to this one. So it will be force of the spring downward. So here what we can say is mass times gravity. Oh no, this is wrong. So this is supposed to be positive force of the spring because it's going downward. And this is supposed to be negative. So now mass times gravity plus, correct, the spring constant times how much this thing is being displaced, which is y, which is minus 0.05, minus k times how the y stretch that we have, because when it was in equilibrium, here when it was in the equilibrium, the force of the spring exerted a force in opposite to the direction it's being displaced. So that's why we have a negative in here. And here we didn't forget about this negative. So here the mass times gravity plus k times y minus. And here we can replace the y stretch with the relationship we had in the previous slides. Mass times gravity over k equal minus m times acceleration. So the k here cancel with the k, and we can rewrite this equation. K times the y stretch, how much is being displaced, minus mg equal to minus m times acceleration. Here, mass times gravity, and now we will open the parentheses. That's what we did in here, and that's what we did in this step. Next, the mass times gravity will cancel with this mass times gravity, and we can rewrite this equation by moving this equation to the other side, and it will give us this equation. So now we can divide the mass in both sides of the equation, as we can see in here. So here the mass will cancel with the mass, and we can rewrite the equation, the acceleration plus k over m times y equal to 0. So here we can replace the natural frequency. As we mentioned in the previous slides, k over m is the square root, is the square of the natural frequency. So, and that's what we have in here. So this is our equation. Just like the previous problem, this is our ordinary differential equation, homogeneous equation, and these are the general solution that we got for this differential equation. And now what we will do is we will use the initial conditions that we got to plug it in these equations to find the integration constants. So the position at 0 is minus 0.05 meter, and the velocity at 0 is 0 meter per second. So when we can plug the values in the position function in here. So here we will be solving for, so remember, cosine of 0 is 1, and the sine of 0 is 0. So here we can get rid of the a, and we can find the b value to be minus 0.05. So here we can solve for the natural frequency, k over m. K is 800 Newton over meter divided by 2 kilogram equal to 20 radian per second. Now we will plug in the natural frequency and the velocity at 0 second into velocity equation, and that's what we will have in here. And 0 times anything, it will give you 0. And remember, cosine of 0 is 1, so here we can solve for a, and b will be cancelled. So here a will equal to 0. Okay. So now we have a, we have b, we have the natural frequency. Now we can plug these three values into our position function, and that's what we have in here. So the position function will be minus 0.05 cosine 20t. So this is the equation that represent the spring and mass with a certain spring stiffness and a mass and a certain block of mass at a certain initial conditions. That is the function that will represent that system with the given initial conditions. That is the function that will represent its position while it is vibrating. So this is the sketch or this is the graph that represent the function, the position function that we have in here. So here we said b is minus 0.05, right? That's how much. So remember, 0, this is your equilibrium. This thing is got stretched upward, negative direction, that's why we have negative, to minus 0.05. A is what? 0. So here we can find again the time. So it starts in here and it complete one cycle and it came back to its position in here, back again, going back and forth. And now this one completes one cycle. So we want to know this system that we have, a system with a certain spring constant, with a certain mass, with a certain initial conditions. If we are given these three things, how much time it takes for this system to complete one cycle? So one cycle is 2 pi equal to natural frequency times time. So time is 2 pi over natural frequency. So here we can find the natural frequency, the period it takes to complete one cycle, 2 pi radian divided by the natural frequency of the system, which is 20 radian per second, and it will give us this value. So that's how much time it takes to complete one cycle. So the frequency is simply the reciprocal of this. So this one tells us that 3.1831 hertz. So what does that tell you? Now this tells us that that this system with this given spring constant, with a given mass, with a given initial conditions, it can vibrate, or it can complete 3.18 cycle in 1 second. Next, we want to find the amplitude, that the highest point that this mass will reach as a linear displacement. So here the C is equal A squared plus B squared. So C is equal to what? A is 0 and B is 0.05 squared. So that will give you the value. We got over it. So now let's solve a third problem, 22-3. So here we are told that we have a spring is stretched 200 millimeter by a 15 kilogram block. If the block is displaced 100 millimeter downward from its equilibrium position and given a downward velocity of 0.75 meter per second, determine the equation which describes the motion. What is the phase angle? Assume that positive displacement is downward. All right. So here we have 200 millimeter, 15 kilogram, and this block got displaced 100 millimeter downward, and it attained 0.75 meter. So now let's write what's given. So spring stretched 0.2 meter. The spring got stretched due to the mass 15 kilogram. Then the 15 kilogram block displaced 0.1 meter. As the 15 kilogram block is displaced 0.1 meter below the equilibrium position, the block achieved a downward velocity 0.75 meter per second. Assume that positive displacement is downward. Here we want to determine the equation and the phase angle. All right, so this is our spring. This is the natural spring length, the original spring length, natural length of the spring. The spring got stretched due to a hanged mass of 15 kilogram, and it got stretched an amount of 0.2 meter. So we know the spring, how much is being stretched. We know the mass that this spring got stretched due to. So now we can, all right, so here is your equilibrium position, and now we can zero the position, and downward is positive y direction. Now we are told that the spring got stretched or pulled downward with the mass of 15 kilogram, a 0.1 meter at 0 second. And as we are stretching down, it attained a velocity of 0.75 meter per second, just like the first problem. I mean, similar initial conditions as the first problem. So the force of the spring will exert a force opposite to the direction of the displacement. So first thing what we will do is we will draw the free body diagram for the spring and mass at equilibrium position. So here the 15 kilogram will have the downward velocity, positive y, and it's going downward. So it will have a positive acceleration, mass times gravity, and it will oppose the direction of the movement, force of the spring. So here we can say that the sum of the forces in the y direction equal to mass to 0. So here mass times gravity minus the force of the spring equal to 0. And remember that it's positive mg because downward is positive and force of the spring is upward is in the opposite direction. So mass times gravity is the spring constant times how much the spring got deflected due to the hanged mass of 15 kilogram equal to 0. So now we will move this to the other side of the equation. It will give us mass times gravity times ky stretched. So now we can get two equations in here. The y stretch, we can solve for y stretch, or we can solve for the k value in here. Now in here we will solve for the y stretch. So y stretch is 0.2 meter when we plug in the values of 15 kilogram times 9.81 divided by the spring constant that we are finding its value. So the mass is given, the gravity, and the y stretch is given. So now we can solve for k, which is 735.75 Newton over meters. So that's how stiff the spring is. So now we're going to draw the free body diagram for the spring and mass where the spring is and the spring and the mass is moving, right? So here we have your 15 kilogram, positive y direction, and it's going downward, positive acceleration, the force due to gravity mg, and the spring will oppose the motion of the block going downward. It will have an upward force direction, force of the spring. So here mass times gravity minus force of the spring equal to mass times acceleration. And remember, the force of the spring is the spring stiffness times the total amount the spring got stretched. So mass times gravity minus k times y plus k times y stretch equal to mass times acceleration. So y is the amount the spring got displaced from equilibrium position, and y stretch is the amount the spring got stretched due to the hanged block. And now this minus sign, we want to get rid of it. So we will, distribute it into the parentheses. So mass times gravity minus ky stretch equal to mass times acceleration. We can replace the y stretch in here with the previous slide relationship, which is this one. So we said that y stretch is mass times gravity divided by k equal y stretch. So we will use this relationship and plug it in here. So mass times gravity minus ky minus k m times g over k. So the k value will cancel with this k value. So here we can rewrite the equation mg minus ky minus mg minus m acceleration. So the mg in here will cancel with this mg in here. And here the spring minus ky will move to the other side of the equation to get rid of the negative sign. So mass times acceleration plus ky equal to 0. So now what we can do is we can divide both sides of the equation by mass. And that will give us mass times acceleration over mass plus k over y over m equals 0. So the mass will cancel with the mass, and we can rewrite acceleration plus k over m times y equal to 0. And here, just as a reminder, the natural frequency is the square root of k over m. We take the square of both sides to get rid of the square root. So we'll get the natural frequency squared k over m. So now we can take this natural frequency and replace it in here. So that will give us right here is acceleration plus the natural frequency squared times y equal to 0. So again, this is your differential equation. These are the general solution for this differential equation. And here we will use the initial conditions that we have in the problem at time equals 0 second. And here we are told that at the position at 0 is 0.1 meter and the velocity at 0 second is 0.75 meter per second. And here, and also from the found and given values, we can find the natural frequency of the system to be 735.75 Newton over meter divided by 15 kilogram. And this will give you 7 radian per second. We will plug in the y value at 0 second and the natural frequency into the position function. 0 times anything will give you a 0. So here we will solve for the b, because remember, cosine of 0 is 1 and the sine of 0 is 0. So here the sine 0 will be 0. So b will equal 0.1. And now we will use the initial velocity or velocity at time 0 and the natural frequency in the velocity function. And we will plug in these values into the velocity function. And remember, cosine of 0 is 1. So we will be solved for a in here, and b will cancel because sine of 0 is 0. So 0.75 equal a times 7. So that will give you a value of 0.107. So now we can plug in the b, a, and natural frequency into the position function to give us this function that represent the position function of the block. So with a given with the given spring constant, with the found spring constant, with the given mass, and given initial conditions, that is the function that will represent the vibration of this system. All right, so this is your function in here, and in this function is being represented in the red function right here. And when and here we are asked to find the phase angle. So the phase angle is simply the inverse tan, the b constant over the a constant. And the b constant we said is 0.1 and the a constant is 0.107, and that gives us 43 degree. That is the phase angle. So, or we can rewrite this equation using the general solution equation to be 0.146 sine 7t, 7 is the natural frequency, plus 0.757. This is 43 degree in radian. So that will be your phase angle in here. Now this this y, this function right here is your red function. This function in here is your blue function. I should written this in blue. That's my mistake. But what I want to show, when your phase angle is 0, that is how the function will look like. So when we talk about the phase angle, this is what we're talking about, this shift. So these initial conditions made the shift to the left from here to here. That is your phase angle that we're talking about right here. All right. Now this is the fourth problem, 22-4. Here we're told when a 20-pound force weight is suspended from a spring, the spring is stretched a distance of 4 inches. Determine the natural frequency and the period of the vibration of 10-pound force weight attached to the spring, to the same spring. So what is given? Here we given a weight number 1, W sub 1, equal to 20-pound force. Okay, so the weight 1 suspended from spring number 1. Due to the suspended weight 1 on spring number 1, spring number 1 stretched equal to 4 inch. Now weight number 2, W sub 2, equal to 10-pound force. The weight 2 suspended from spring number 1. In this situation, we want to know the natural frequency and we want to find the period, the time it takes to complete one cycle. All right. So here we will talk about the spring number 1. So this is your spring number 1. That is the natural length of the spring. That's your spring number 1. Now, for spring number 1, got stretched due to the hanged mass of 20-pound force. That is its weight. Weight 1. And downward is positive, and it got stretched an amount of 4 inch. All right. So now this spring and mass is at equilibrium position. Now the same spring number 1 that we have, okay, where it have its natural length of spring, that spring number 1 got stretched due to a different weight of 10-pound force, W sub 2. And due to that, it got stretched a certain amount. So now and reached to equilibrium position. All right. So now let's draw a free body diagram for spring number 1 and weight 1. So 20-pound force, which is our weight numbers, weight 1, it have weight due to gravity, which is mass times gravity, which force, mass times acceleration, and the force of the spring that opposes the deflection of the spring in the downward direction. And we said downward is positive y. So here, the sum of the forces in the y direction will equal to 0, because at the equilibrium position. So downward is W sub 1 minus the force of the spring equals 0. The weight is minus K stretch equal to 0. So here, K1 is 60-pound force over feet. So weight 1 is equal to K y stretch. Weight 1, y stretch equal to K. So K is 20-pound force divided by 4 over 12 to convert inch to feet. And we got the 60-pound force over feet. So now we will talk about the spring number 1 and weight 2. So the mass times gravity, go to the other side, and now we got this mass, which is in sludge, 0.3105. So K1, we know because we're dealing with the same spring, 60-pound force over feet. Here the natural frequency will be, we want to find the natural frequency, which is K over M. K, we found it to be 60-pound force over feet divided by the mass we found in sludge, 0.3105 sludge, and that gives us 13.899 radian per second. Now we want to find the period. So what is the period? Period is 2 pi over the natural frequency. Now we can write 2 pi and we can get the reciprocal m over k. So it will give us, we plug in the values that we found. And for this system to complete one cycle, it takes 0.45 seconds. So here let's discuss a little bit about natural frequency. And what is a natural frequency? Every object, for example, let's talk about aluminum. Now, if you remember that, every material have its mechanical properties. So when you, let's say, stretch an aluminum bar, the aluminum have elasticity. So what is elasticity? Elasticity means that is how much you can apply a certain force or a certain pressure by pulling the aluminum bar to a certain level, and when you release that pressure, that force on the aluminum bar, the spring will go back to its original position. But the reality, it will return, but what will happen, that aluminum bar will vibrate. Now, every object or every material have its own natural frequency, and that natural frequency of that system depends on the how elastic the system is and the mass of the system. So as I mentioned before, uh, the fork, due to its material, due to its mass, when you hit it, it will start vibrating, right? That the spoon have its own natural frequency, and we can represent a certain mechanical system or a dynamic system as a spring and mass model. So instead of the elasticity, we can say the spring stiffness K, or and instead of the mass of the aluminum bar, here we're talking about the mass that's being hanged from the spring. So that what is natural frequency is. Now, also you can learn about what a natural frequency is just by looking at the units. So here we want to know, what does a spring mass system do? It oscillates. So when we say oscillate, what does oscillating mean? It means it move or swing back and forth. So here we're talking about linear motion, representing it in a circular motion. In the previous slides, when we show the spring and the mass is moving linearly in the vertical direction, right? But when we represent in a function, we use sine and cosine, and we use radians and degrees. Why? Because here we're dealing, because when you start from a position and you move and go and come back to that position, then we can represent this position as a circular motion, and we can use these things. So in here, so let's take a look at this. So here you have your spring as this rod, and this is the mass that you have in here. All right. Now this spring will move upward. The spring is being, pulls the mass upward. That's the maximum amount this spring got compressed. And then the spring will exert a force downward to push the mass downward back to its original position in here. So it went back and forth. It started from this position and it ended at the same position in here. So if you think about it, we start so at this point right here and this point right here. So that's why we can represent. So for example, Let's say this position where I have a circle in here is this one here. So it went all the way back and we returned back to this position, to this exact same position. So that's why we can deal with it as a spring. So this theta right here is the radiant that represent the arc. Right, so that's why the period is 0.45 second, meaning to complete this one cycle takes 0.45 second. Now remember, the arc represent this one represent the linear, A represent the linear movement. Theta is the correspondence for the linear movement, which is in radian. So it takes 13.889 degree radian. It moved this amount in 1 second. So that is like a velocity. So here the natural frequency is 1 over the time it takes to complete one cycle. And the natural frequency tells us that this system that have this natural frequency with a given initial conditions, it can vibrate at a rate of 2.22 hertz, which means 2.22 cycles per 1 second. All right, problem number 5. So when a 3 kilogram block is suspended from a spring, the spring is stretched a distance of 60 millimeter. Determine the natural frequency and the period of the vibration for 0.2 kilogram block attached to the same spring. So here we have a mass number 1, M1, equal to 3 kilogram. So M1 is suspended from the spring number 1. Now, due to the suspended M1 on spring number 1 stretched 0.0 meter. So mass number 2 is 0.2 kilogram. So mass 2 suspended from spring 1, just like the previous problem, we are asked to find the natural frequency and the period. So here we have the spring number 1 right here, and spring number 1 got stretched due to a hanged mass of 3 kilogram. Okay, it got stretched an amount of 0.06 meter, and this is your equilibrium position. Again, the spring number 1, same spring as in this case, got stretched due to a different mass of 0.2 kilogram. It got stretched a certain amount to the equilibrium position. So here the natural frequency, which is this, for spring number 1 and mass number 2 system, and here we are asked to find the period for spring number 1 and mass number 2 system. So the natural frequency is what? Is K of this. So we said that the natural, here we want to find the natural frequency for the spring number 1 and mass number 2, and we hang the mass number 2 on it. So here we want to find so we were given the mass 0.2, but we want to know the K value. The period for spring number 1 where a mass number 2 is hanged on it. So spring number 1 and mass number 2 system. And here what we want to find is the natural frequency of the system. And we will get this by finding the K value. So the free body diagram for spring number 1 and mass number 1 is 3 kilogram, positive y direction downward, mass due to gravity, and the spring will have an opposite to the displaced or the stretched the displacement. So the sum of the forces in the y direction equal to 0. So that's mass 1 times gravity minus the force of the spring equal to 0. So m1 times g minus k1, which is the value that we want to find, times y stretch equal to 0. So mass times 1 times gravity equal k sub 1 times y stretch. Now we can solve for k sub 1 by moving y stretch to the other side of the equation, and it will give us this equation. Now we can plug in the values that we have for mass 1, which is 3 kilogram, and the gravity, which is 9.81 meter per second squared, and the y stretch, we are told that the amount is 0.06 meter. Plug this into your calculator, and you will get the K1 is equal to 490.5 Newton per meter. So that's how stiff the spring is. So now we can plug the K value in here. All right, so here we set the natural frequency for spring number 1 and mass number 2. And here we want the period for spring number 1 and mass number 2. So here the natural frequency, we got it by replacing the found values, got 49.52 radian per second. And the tau is 2 pi over 49.52 radian per second. And when you plug this into your calculator, it will give you 0.127. That's how much it takes to complete one cycle.